The recording started. Welcome back. I haven't seen you since long time, I believe. Maybe you missed me, or maybe you are happy not having lectures. Anyway, we'll start back. Before starting, I would like to remind you the last time that there is a midterm exam tomorrow at 11 a.m. Get prepared, study well, and again, I remind you also that there is a prize for the one who or get the highest mark. Whether they are one person or two person, all of them gonna get a prize or a present. So I think last time we stopped somewhere in migration. We talked about diffractions, and we say that diffractions are actually can be removed by process called migration. Migration is really an expensive process. In terms of expensive, I mean computationally expensive. It takes a huge amount of time for the computers to process the data for the migration or to do migration process. And the effect of migration, it removes diffractions. It removes or collapses diffraction energy to the point they are generated from. For example, the image you see, this is a repetition. Actually, I'm just repeating myself. I believe I completed this part the last time. So here, the upper part, upper figure is showing a point, but the point is depicted as a diffraction hyperbola. After migration, all of the energy will be collapsed back to the point it diffracted from. That's the diffraction point. It's only one trace. Anytime, if you have any question, please stop me. I shared the jump. If you have any questions related to the topic, please stop me, send a message. I'm watching the chat here, and speak out if you don't feel shy. I think I completed this part too. So here, another image too, showing a seismic section that's almost the final product, but before migration. Some artifacts we find are those diffraction hyperbolas. They are happening along discontinuities. So here I'm having a certain horizon or a reflection. Keep in mind that this is in two-way time domain. The vertical axis is two-way time domain. This is the distance. It's from one trace to another trace. Whenever there is a discontinuity, some diffractions happens. They can be collapsed or removed by applying migration. If I keep moving back and forth between these two, you will find that it's way easier to follow the horizon in this migrated section rather than the unmigrated section. Your task usually as a geophysicist or a geologist, or even maybe, I'm not sure, probably a petroleum engineer, to follow these horizons. That's actually also the task you will be asked to do for the project, the upcoming project you will have. We see how many people, 28 maybe. So your task for the project, we'll make more explanation about it soon, is to follow those horizons. Again, side by side, way easier to make interpretation on this section rather than to the one to the in your left side. So in my left side, not sure. Maybe they are swapped for you. Another section, that's stack section. This is before, that's after. So a feature you will find are those bow ties. You see these bow ties? They are diffracted back to synclines. So this is syncline, another syncline. Synclines generate a feature known as bow tie. This is a bow tie, another bow tie. This is in here some discontinuity, they are corrected. Static correction. Static correction is a process usually applied during seismic data processing. It's a cumbersome process. It's not that easy. It involves a lot of picking. Uh, to do it, usually there are different techniques to do a static correction. The main two techniques is uphole survey. You make uphole survey. Another technique is a refraction. You do refraction. The aim is to remove the withered layer and keep the unwithered layer and bring the seismic to a datum level. What I mean by datum, at certain depth. Anything, yeah, the trace is starting the zero, the trace zero going down. Seismic section is going down and increasing in time, in two-way time. So this zero time is usually along a datum. The datum is defined during the processing. When they define the processing, then they say what datum I should make. In Oman, usually they make it like 400 sometimes, and sometimes 150 meters in Oman, in the southern and western, in the southern and central part of Oman. So there is a datum. Actually, in your seismic data, if you find a lot of glittering, a lot of discontinuities, it means that the data were not corrected for static. No static correction have been applied. Why is that? Because this small variation in the elevation between shot and receivers, or these low velocity layers, this is very low velocity. For example, in Batna region, most of the Batna region, the top layer is a soil layer. It goes up to a depth about, let's say, 150 meters, 60 meters, within that range. So I need to get rid of this column, the unwithered layer. I need to bring almost all the shot and receivers to the same datum. That's what we call static correction. That's what you need to understand for the time being, what is static correction, without going into the details. So this is a real shot, but how they correct them, as I said, you need to know the uh, the thickness of this unwithered layer. Sorry, the withered layer. I make usually this mistake. The thickness of this withered layer, you need to know it. The velocity of this withered layer. How it can be done? One technique is refraction. In your last lab, I believe, you did some type of refractions and you got a layer, the depth to the second layer, and the velocity of the top and bottom layers. You can apply the same technique here. They do usually also alongside seismic reflections, they do refraction as well. Another thing probably is to drill, to make a drilling somewhere. Why those drilling are, why they do them? Because you don't drill very deep. You don't drill up to 1 kilometer or 2 kilometer or even 3 kilometers. In Oman, in the new discovered gas fields, they're drilling up to 5 kilometers, 4 kilometers. You just drill up to like 100, 150 meters, and it will give you a direct estimation of what type of layers you are having. The people who are drilling, they get the samples coming. The drill bits bring the samples to the or cutting to the surface, and you can touch them. You can get an idea what type of rock are they. Is it a hard rock? Is it a soil? And it gives you a control point, at least exactly where the depth is. You can combine both of them probably. You can combine upholes, these things, or drilling, they make small drilling, they name them upholes. You can combine it with the refraction. At least it will confirm your results from the refraction survey. Because as we know, geophysics is associated with a lot of uncertainty. To remove the uncertainty, the best way is to drill. to make a drilling and confirm your results that the layer thickness at this specific point is that much. Overall, the idea here, we need to bring seismic to a datum level. This can be done through static correction. We apply static correction. Here comes a question. What do you think about a marine survey? Is there any static correction in marine survey? Let me ask Ala. She was the first to come to join. What do you think, Ala? Do we do static correction for marine data? Seismic marine survey? You can type, expecting an answer from you. So we say land data needs land data need static correction to bring the data to a datum level. The datum level is that like the shot and receivers are all in the same level. So the zero time in my seismic section, this zero time is the datum level. This datum level is a certain depth above or below sea level. It's either 400 meter below subsea, sea level is zero everywhere, or above the sea. Even they can make it above the sea. In marine, actually, there is no static correction. In marine surveys, we don't apply static corrections. We do a static correction for a land survey. Why for marine we don't do a static correction? Because they are already on the same level, and the line, the acquisition line is at specific level, usually below the sea level, below the sea surface. So there is already a datum established. And that's the reason I don't need to apply static correction then. And mostly sea bottom or sea floor is not very unweathered layer. It's somehow hard layer, most often. It's an ancient layer. So I don't need to apply static correction for the marine data. The question here, the answer for this question, no, there is no static correction for marine data. So if I compare what is before the static correction and what's after the static correction, so I'm having, you see this line, I'm having two velocities, V naught, V sub dot, and V sub 1. They are two different layers, and I need to get rid of this one. You make first the decision that I need to bring my data to this datum, whatever this datum is, 150 meters, 400 meters. It depends on many factors, how high you are, how thick is the unweathered layer is, but bring it something below the unweathered layer. Oh, sorry, below the weathered layer. So it's supposed to be all of it below this layer. This the top of second layer. That's the top of second layer, and that's the top of first layer. That's the Earth surface. Bring it something like that. And finally, there is no glittery, there is no mismatch between the traces because of this low velocity layer, topmost low velocity layers, or even the variation in the heights of these receivers. So this is another receiver, for example, this is one receiver. You'll find they are at different elevations. These things will create actually some mismatch between traces, seismic traces. To correct this mismatch, do static correction. Apply static correction to your land data.
Doctor,
Yeah,
I have a question.
go ahead.
You said that there is no static correction in marine, but what about tide effects? Even if the line of acquisition is fixed, there is a chance to move it.
Uh, but they keep it like 6 to 10 meters below sea level or below sea surface. So there is usually minimum tidal effect. There is another effect they corrected. They call it feathering. I didn't want to go to that level, but feathering is that maybe when you are moving, some tides hitting your, the tides are coming from one direction, are hitting these streamers. Streamers are cables filled with some type of fluid, and inside them, those, the hydrophones are placed. So they might come and move this the cable line from the ideal line you made during the planning. So those small variations they corrected through a process called feathering. They could do a different type of correction. That's true for tidal effects, but it's not due to, it's not like static correction. Static correction usually quite difficult, especially in the Middle East, in UAE, Oman, Saudi Arabia, even in Kuwait. The reason being there are sand dunes. There are a lot of sand dunes. I believe you know what sand dune. Hudban Ramliya. They keep moving, and their velocity is very, very low. The velocity of these sand dunes are almost like 200 or below 300. They will create some artifacts on your data. You need to get rid of them. And it's a big challenge actually. Do you remember the last video? They said we made the acquisition within 2 months, but we do the processing in almost a year or even more than a year. The processing takes huge amount of time. They collected like, if you remember the video, we watched it together the last time. He said we acquired a data having a size of almost 71 terabyte. That's a huge amount of data. It's a huge amount of data. It takes a huge then time to process. Going back to the survey types, there are two types of survey usually. Their planning is different. The acquisition type is different. The source is itself is different. Geophones or the sensors are different. So we can categorize these surveys as two types. One of them is land survey, and the other one is a marine survey. Mm, may I ask a question? Which one you think is faster and cheaper? Marine or land survey? Which of these two survey types, land or marine, is cheaper? Do you understand what I say?
I think land surveys.
Do you think land survey is cheaper? Uh, Safia, she's saying land survey. Do you agree with her?
I think land survey also.
Land survey. So you see in land survey, you need to move the geophones. You need to move your vibrators. But in marine, everything is tied behind a vessel. They name it a vessel, but a ship. Seismic vessel, it's a ship, big ship towing behind it some seismic lines. So there are lease workers or lease work involved in terms of moving geophones from one place to another place. It's almost like 10 times cheaper than the land survey, acquiring the same amount of data with the same amount of aerial coverage. So usually marine actually is way, way cheaper. And that's the reason they explored or made seismic surveys everywhere on marine, almost. But land is not that much accessible. Can I go above a mountain and do seismic survey? It's not easy thing. Vibrators cannot move there. There are some other logistic difficulties. In marine, you can easily ask the fishermen stop today catching fish. for 2 days or 3 days or even a week or even during a time of the day. Maybe you do your survey during night time. But in land, maybe at some location there is a valley or there is a wadi or there is some buildings. So you take those things into considerations. Any small change you make during the planning stage, the planning is the perfect stage. The ideal stage, you acquire your data having some certain scenario. My phone supposed to be here, my shot supposed to be here. But when you go to the site, you'll find no, actually there is a home, someone having a home where I supposed to make my shot. You make an offset then. You make a small change to your initial plan. These small change make a lot of effects to your data quality. And to improve then those quality, you need to do a lot of more processing. You say, we already know that we don't do static at least for marine, but there is a static correction for land survey. Static is a difficult process. The companies, they charge a lot for that. The processing companies, for example, in PDU in Oman, the biggest processing company is a company called CGG. I'm not sure what it stands for, but the name is CGG. They employ a lot of money. They employ even a lot of ladies. Maybe they prefer ladies because ladies, whenever they join them, they don't run later on. But boys, they employ them. After they get experience, they go and get another job somewhere else, PDU, maybe Oxy or any other company. So in general, land survey is way more expensive, almost like 10 times more expensive than marine surveys. So this is a marine survey. You see that the geophones are inside like a tube. This is what we call a streamline. That's streamline. It's filled with oil, with some type of fluid. And the cost is basically dependent on the length, on the area you cover. The bigger the area, the higher the cost gonna be. And they are the sensors are actually called geophones. Instead of uh, being responsive to change in elevation or change in displacement or in velocity, change in displacement is giving you the velocity. Change in velocity gives you what gives you. If there is a change in velocity, what the parameter, physical parameter you get?
Acceleration.
Acceleration, yes. So change in displacement gives you, I'm hearing some kid talking. Is she your daughter? No problem. So we use hydrophones for marine surveys, and the streamer line is ideally kept along a certain depth. But as I said, there are some changes or there is some effect from the tides, sea tides, and we need to correct that. Here, for example, in land survey, each point, either it's a geophone or a shot point, VP point, vibrator point, you need to survey it. You need to take a GPS there, advanced GPS, and record its XYZ location. Whereas in the marine, you just tie behind there at something called tobo. It has two functionality. One functionality to keep the stream at a certain depth. Another functionality is to record the location, XYZ location. Yeah, instead of going everywhere, surveying every point, as is the case for land survey, here now we just use something called toboy, and we tie it behind the end of the streamer. As I said, it has two functionalities. One of them is keeping the streamer at specific depth. Those are geophone numbers or hydrophone number, 1, 2, 3, the number or receiver numbers. That's the streamer. This is the shot point. If you go back to the video, you'll find they use array of sources. The most common one is called air gun. Air gun purpose is you release high pressure air stored in a chamber at high pressure. You release it suddenly, so it has huge amount of pressure. 100 psi or even more. That's like 5 times the pressure released from a pistol. You, you fire a pistol, that's almost 5 to 10 times higher energy released than a pistol. So it's really, really huge amount of energy. There are other types: sparker, water gun, aqua pools. Do you need to remember them? No. Why you need to remember them or what they are? Unless you use them, then you need to know how they function and how they work. But in general, there are multiple types of sources. The most common is air gun, and they found that the air gun is more environmentally friendly. It has least effect to the mammals, marine mammals and animals. So going back then to land survey, as I said, it's more expensive, it's more tedious, it's more time consuming. The survey you acquire in 2 months with a specific area in mind. In marine, it probably will take you 10 or a year in land if you apply or you do the same survey in land. As well, we have a lot of different type of sources. So we have like explosives, dynamites. We have such thing, we call it drop weight. They raise a weight, a heavy weight, to a certain height and drop it suddenly. Finally, the most common and most one used nowadays is Vibroseis truck. That's a truck which keeps vibrating and generating energy. So we make this distinction between these two types: impulsive or non-impulsive. Whenever I say an impulsive, the energy is released just suddenly within very short time. Something like so if I make a drawing here of this impulsive, so this is the amplitude, the energy release, the amount of energy or amplitude, that's time. So impulsive, you release it, it goes something like and drops back. That's the source function, source time function, they name it. That's how is it. But the vibrator is different. Vibrator, you are shaking all the time. It goes like that. It makes that type of sound. It goes and it has a characteristic, we call it sweep. The characteristic is a sweep. So it starts with low frequency and increases the frequency, something like that. You'll see some example. But this is, we call it either impulsive or non-impulsive. This is impulsive, this is non-impulsive. Impulsive, it's a source function characteristic is short period. Whereas for the Vibroseis has something we call sweep. That's what meant by impulsive and non-impulsive. So wherever you put your geophone, it's not single geophone. They tie together like almost 12 or 24 geophones in one point. They give you one trace. It has many advantages. Yes, maybe impulsive is like heartbeats. It has short span of time, but Vibroseis is continuous. It's starting from low frequency to from almost like a frequency of 6 hertz to 80, 100 hertz. That's the range for the sweep, and it vibrates for almost like 6 seconds, 5 seconds. The sweep length will come soon to this point. I'm answering a question from Saeed. His question was like those of like the heartbeats you find in hospital. Tick, tick, tick. Yes, maybe the impulsive. But the data usually you get is the final image you get is the same. We like vibrators because they are not damaging to the environment. One of the things you don't need to make holes for dynamites. You need to make a hole like 50 meter, 40 meter. Put the dynamite there in the hole and fire it. If for any reason a mistake have been done, you cannot repeat it easily. But the story or for the Vibroseis is totally different. If you by mistake you made a mistake or was in a hurry and ran something, or there was some noises nearby and you wanted to repeat the survey or repeat the shot, for the Vibroseis that's really easy. That's more easy. It's more controllable than the dynamite. My point here again, I want actually to put more than one geophones. It has certain impact. You increase the signal. And another thing, it's very effective removing, making like an array of geophones, not single geophone. At one point, it has the effect of removing ground rule. What's ground rule is surface wave. Why they name it ground rule? It's like the way it moves, it's grounding the surface. It's moving like grounding the surface. So that's in oil industry, they name it ground rule. And the people who are doing processing for data, oil industry data, seismic data from oil industry, they name it ground rule. Seismologists, other seismologists who are interested in earthquake data, they name it surface waves. So, but they are the same actually. Ground rule a bit hard to remove during the processing, but to minimize their effect, deploy your geophones in a way. I don't want to go to the details, but deploy them or make their surface array the way you plan them on the surface in a certain configuration, so the effect from ground rule is minimum. You try to suppress the energy from the ground rule. Last point here, that their cost is usually so high. The land data acquisition is really expensive. It's not the expensive is coming from many things we already described. Also, the processing is more expensive too. You have to do many more things like um, static correction, which is not applied for marine data. Those things, the extra steps you need to follow will add to your expense. You need to pay more money if you are working for PDU or Oxy. Those are operators. Operator companies usually they don't themselves have seismic crews. They go ask other companies. Schlumberger have seismic crews. Other companies, I don't know their names, but I did my summer training with Schlumberger, and the section which I do seismic survey is called Western Geco, at least in Schlumberger. There are other Chinese companies nowadays, a lot of Chinese companies, maybe they ask for lease money. That's the reason they bring make contract with Chinese companies. At least the one I know doing for PDU the last 5 or 6 years, seismic acquisition in Oman. That's the shape of a vibrator. This is the Vibroseis. That system is Vibroseis. When they deploy it, when they start sending the energy to the ground, it it raises, it tires, it push all its weight on the Vibroseis. If you go back and watch those video links for either marine and land surveys, you'll find what they do at the time they are deployed, at the time they send the energy to the ground, either front tires or back tires, they are lifted from the ground to put more weight on this equipment, on the Vibroseis. There is good coupling then. The coupling between the ground and this plate, the plate you see here, is perfect. Then the energy is sent to the ground. Here is what I name the signature of the energy, or the signature of the wave sent by a Vibroseis. So it's a sweep. They name it sweep because if you track this change in amplitude, you will find its frequency is increasing. The distance or the time from peak to peak or trough to trough is decreasing. Since the frequency itself is increasing. So it has frequencies not from one, maybe. Nowadays they can go, but they can be even 60 seconds, 10 seconds, 12 seconds, that much. It depends on your acquisition parameters, basically, and how deep you want to acquire. So you can change those parameters, make it like 6 to 81. The wider it is, the wider, the better is it. The wider, the better your data gonna be. But there are other parameters come into control. I don't want to go into depth. The idea here is that the sweep looks something like that. And the energy will be recorded, they retain as such. So if I make my drawing again, let's see, where is my drawing? Jamboard, here is. Is there, I clean everything? Not sure.
Yes, doctor, at the top.
Where?
At the top, clear frame.
Clear, yes, thanks. That's good. So if I make like an explanation what you are seeing here, back to the slides, what are these two things? I can explain them simply as such. So let's say this is my surface, this is first layer, this is second layer, and the energy went down. After some time, it was recorded. It was recorded here. It's going like that. Recorded here. This one recorded here. But the energy signature of the energy is actually a sweep. So the one recorded from here is ideally similar to your sweep. That's the energy you are receiving back. That's the one you sent. And this is the one you are receiving. The amplitude gonna be smaller. And the amplitude gonna be smaller a bit because it traveled. It wasted some energy while it's traveling. The deeper it goes, the farther away it goes, the more amplitude lost. Amplitude is related to the energy. How high those peaks or troughs are, we call them amplitude, but they are related to the energy, to the amount of energy. So this one, after some time, if I make my timeline, this maybe comes after some time as such. This at later time as such. This is your sweep. And how high, how small are they? It also depends on the acoustic impedance, VP. V times density of respective layers, V1, V2, 2, V3, rho 3. So how strong they are, it depends on acoustic impedance. Could you tell me very, very strong reflector usually we find in seismic data? The acoustic impedance is usually so high between at that reflector. Who can tell me? Who can tell me what that reflector is? Any idea? Seabed. Seabed is really, really strong reflector. If I see some image. So you see this is on sea, on marine. This reflector, seabed reflector, is really strong reflector because the acoustic impedance, the change in density and velocity between the sea itself and the rock is so big. This is strong acoustic impedance. So the amplitude you see here is strong. This image is basically a lot of traces nearby each other. There are a lot of traces nearby. You will come to that soon. But in reality, what happens? Yani, if I keep recording these things, they becomes on top of each other. Yani, when I record one time, this time is plus this time. If I have a lot of reflectors, total mess then. How they resolve this thing? They resolve it through a process called cross correlation. So here is my signal. This is my sweep, original sweep, or the energy sent by the vibrator. This is the reflection from one layer. This is the reflection from one layer. This is deeper layer, and that's another deeper layer. The three interfaces. 1, 2, 3. How small, how big they are depends on many parameters, as I said. How strong. They cannot be higher than this one. Their amplitude cannot be higher than the original sweep. But I add them together because the time I'm reading all the time, I cannot separate them. I does not know when the other reflection cap happens. This is still arriving. This one come. What they do a process called correlation. Correlation between the sweep itself and this recorded trace, this recorded data. What's correlation? You don't need to know. You need to know just the term correlation. You can go search for correlation because it's not just applied for seismic, it applied for many things in signal processing, in satellite data sending, in electrical engineering, in many fields. And the geophysicists, they haven't invented it. They are just using what's already available, what's used by other disciplines like electrical engineering, signal processing, many other fields. So once you correlate this one with this trace, you get a nice picture, a nice trace. So this is the reflection from, that's the reflection from first layer interface, second interface, third interface. That's exactly are those things you have seen here. So your trace becomes something like that. There is nothing. After you correlate all their sum, these two, they sum them, long like trace. You correlate this one with your original sweep, you get a trace, a nice trace. That's what, as a geophysicist, then you can easily interpret this. You say, okay, I'm receiving the energy is reflected back. This energy is from an interface. Interface is a boundary between two different layers, having a different acoustic impedance. So this is another interface, a third interface. You see the polarity is changing. This is up, this is down, this is up. This is what we call polarity, by the way. It changed for a reason. Here is the real data. It's a real data. This is your sweep. It's from 0 to 10 seconds. And you let your GPhones record for 15 seconds. The GPhones record for 15 seconds. It's moving from 1 second to 6, 5, from 5, 6, 7. Or you get some record which is not very useful. However, what you do, you correlate this thing, the sweep itself, with this recorded data with 15 seconds. So this is 10 seconds. This is 15 seconds. Your final record, the correlated shot record or correlated shot together, going to be 5 seconds. At least here, before the processing, at least I see some reflection, some hyperbolas. Those hyperbolas are indicating that there is an interface. There is a change in the acoustic impedance between two different layers having different acoustic or geophysical or physical characteristics. More for the processing might make it better. Maybe you need to remove the diffraction. Maybe so, not diffractions. Maybe you need to remove the direct and refracted energy. The one you see here, they are direct and refracted. You need to make some noise removal. It becomes for them better and better. But what are they? How they process? That's not a scope of this course. Usually shot together, if I compare this final record you see here with the ideal cases, that's what you get. So you get the direct wave, the direct arrival. The direct arrival is basically this one. For example, if this is a layer, that's the shot. This is the receiver, that's the direct. It's not the air, it's moving in the layer, in this first layer, but within the layer, not in the above the surface of the earth. That's what we call direct. So this is the direct. These are refraction. So in your lab you did the first lab, not this one, not the second one right now you are working on. You were given one side. You're given, there are two sides because the shot is in the middle and the GPhones everywhere, to the right and left. The shot in the middle and the GPhones are spread out in both directions. So you were given one part only and you did your picking. You're at least, you did manual picking, drawing a line, straight lines. You can easily draw straight lines because actually the diffracted energy, the refracted energy is a straight line. The direct is also a straight line. Reflection energy is not a direct line. It's more complex. It's a hyperbola. It's not a parabola. You differentiate between parabola, x square, the function y equals x square. That function is a parabola. But this is a hyperbola. Its function is a bit more complex. But they will generate such features. The higher their deflection, you see, the higher the deflection is, the lower the velocity you need. The lower the velocity you need to do. You remember we talked about last time move out correction. You flatten them. You flatten them using move out correction. So here, for example, the blue curve, you see, there are a lot of reflections, basically. The blue curve, you see, having a higher deflection than the one you see here at starting almost like 1 point, little bit higher than 1.5. Why is that? Because this is a multiple. This is actually a multiple. What's multiple? Multiple. If I ask you this question, C, this line is C, this is B, this is B, and this one is A. Which one is a multiple? A, B, or C?
B.
B is a multiple, yes. So this reflection will give you a gentler hyperbola. This reflection, this one, it becomes here at that time, it gives you a more steeper hyperbola. But this one, because it's happening at the time of primary, of this primary, it will be recorded at later time, double of this time. Double of this time. It happens here, but having the same velocity as the one above. As the one above. So because its velocity the same, it's traveling in the first layer, but it has taken double the time because it's a multiple. Whereas this one, it's primary. This is a multiple. B is a multiple. C is a primary from the second layer. But it has a higher velocity. Part of it is traveling in the second layer. It has a higher velocity. Hope that's clear. So that's what you see here. The blue hyperbola is a multiple. You find also air blast. What's the velocity of air is almost like 330 meters per second. And the last thing you'll find those things, what we call ground rule or surface waves. They happen to be here in this region. Not having good gather in here, but they will happen to be here. If I show you some gather, let me seismic shot gather, just to show you how the ground rule looks like. Oh, I found one. You see, that's what we call ground rule. They are low velocity, but their amplitude is high. You see, their amplitude is higher than the amplitude you see for the reflections or refractions. That's this part is all masked by this ground rule that happen to be here. If I put them side by side, that's what you see. This is the ground rule. Here the ground rule is. They even sometimes mask the air blast or air wave. If you bury your geophones, if you bury them beneath the earth surface, put some soil on top of them, you minimize the effect or the energy generated by air blast. Hope that's clear. There are some links. I think we have watched already this video, but you can watch it at whatever time you like. But these are the Vibroseis. They work in array, usually 2, 3, or even 4, working in synchronization, sending the same energy together without even small delay between one and another, without even like microsecond delay. If there is that small delay, they probably might repeat the shot. So here you see, wow, so many Vibroseis. You see, do you see this one? It's in operation. The back tires are off the ground. This one also in operation. The back tires are above the ground. because they need to make a good coupling between the plate, the big plate, and the ground. These are the juphoons. In each of these metals, like 12, 24 juphoons. Those are connection cables. The red one you see there, you see the acquisition size is really huge. Is really huge. They are ready to be deployed, to be planted, and the acquisition starts. This is a seismic crew. Seismic crew usually is not attached to the base camp. And in every oil industry, there is a base camp, like let's say Khuwair field or Natah field or whatever fields you probably may have some of your relatives working there. They say we are going to Khuwair. Seismic crews, they are not attached to the base camp. They are separate. They go try to be very close where the operation is, where they are acquiring the data, instead of spending all the day, half of the day, taking your equipment, taking the cars, taking also the vibrators from the base station to the acquisition location. It's kind of time consuming. They start right away. They need to work right away. They keep the vibrators, by the way, there. At least they be safe that we are nearby. We are very close. Our camp, temporary camp they built, is very close. So since this is a temporary camp, they are all caravans. You see, they are all caravans. They are not permanent buildings you'll find usually in base camps or big camp. And Safa field for Oxy, there is a huge camp. And many places and many oil fields, that's the case. But seismic acquisition crews, no, they are temporary in movement. They finish from one place. They try to even be very close where are they acquiring the data. These are some workers. Here they are doing some testing before they deploy the juphoons. These blue color thing or the equipment you see, these are the juphoons. How they display the data? Finally, and once you acquire the data, the raw data, the initial or simplest type of display is this thing, is variable area. It's a normal trace. This is variable area. This is, sorry, this is wiggle. This is a simple wiggle trace, not variable. This is variable area. We'll talk about variable density soon. Variable density usually is the most common one, but people who are working in processing, they try to display the data in this format to at least appreciate the data, to find anything wrong with the data. Maybe this format helps. This is another type of display. They call it variable area. So one area is colored black. The other, the peak, almost all the peak from a baseline, zero baseline, they color it black. So there are traces. This is variable density. Variable density display. This is huge seismic section in marine. Interesting things you find, there are a lot of synclines and anticlines. This is the basement. The basement is actually not sedimentary layers. It's either igneous or metamorphic. The basement rock. Usually, if you do like a geology for Oman or other courses in geology, you know that basement is not a sedimentary rock. Since it's not sedimentary rock, what's a distinctive feature of sedimentary rock? They are layered. They are layered sedimentary. Whereas igneous or metamorphic rock, they don't exhibit this layering. They are massive. So the reflections, there is no layer, there is chaotic reflections. You see here, the reflection is very chaotic. I don't see any layering. Whereas here I see layering because these are sedimentary. These are not sedimentary, they are igneous, metamorphic. That's the basement. And they describe their pattern as chaotic without good shape. That's what I mean by chaotic. But this is also the terminology they use to describe reflections from basement, from igneous rocks or from metamorphic rocks, whereas you find nice layering in sedimentary rocks. So I can even display this thing as wiggle or as variable area, but instead I'm plotting it as a density display, variable density. It's almost like an image. So this is very popular among geophysicists or geologists to type of display of seismic reflection data. Maybe you don't like this white black color. This is very popular color. Maybe you want it more interesting. You make it black, white, green color. They are color scales. So this is another color scale. This is also very variable density, but instead of using grayscale, so that's a grayscale color bar. Gray means black, white only. So one side is black, one side is white. The higher the amplitude, the more black it is, or the opposite. It's fine. Or the opposite. So but here this is almost like a rainbow color. Has maybe in one side there is black, in this side the maximum amplitude it's red, in the middle it's green. You got the point? So if the amplitude is small, lowest amplitude, the color becomes black. If the amplitude is so high, what I mean by amplitude is this thing. If the amplitude is so high, the color gonna be red. There is some red, you see. In between, it's green. In between, it's green. So that's how they display them. There are things you see here called direct hydrocarbon indicators. We come soon to this. What exactly is DHI or direct hydrocarbon indicators? We'll come to that topic soon. But let's talk about reflections, back to the basics of reflections. Do you remember the critical angle? And we already know what's critical distance. If a ray reflected from a distance beyond the critical reflection, we call that total internal reflection. Most of the energy is reflected. However, if the angle of incidence is lower than the critical angle, most of the energy gonna be transmitted to the deeper layers. And what controls also, apart from the angle, acoustic impedance. And the acoustic impedance is simply density times velocity. Density of the rock times the velocity. There are two parameter or coefficients, we name them: reflection coefficient, and the other one is transmitted coefficient. How much energy is reflected back? How much is transmitted down? If we take only, not the angle, only the acoustic impedance into consideration. So it can be worked out using this formula. For reflection coefficient, that's the lower layer density and velocity minus the upper layer density and velocity. It gives you what we call reflection series or reflection coefficient. You divide it by their sum. It's a bit different for the transmission coefficient. It's a multiplication of the acoustic impedance of the upper layer only by 2. It gives you the transmission, how much energy is transmitted to the second layer. However, as I said, These two will be applicable only at almost normal incidence when the ray is coming almost down. They are applicable in these two, in this case only. If there is a big angle, you cannot use these equations. There are other equations, but they are more difficult. That's the reason I don't want to cover them, at least in this course. If the angle is greater than like 20, let's say, but for almost normal, when the rays, the energy is directly hitting the interface at the normal angle, these two equations are applicable. So that's the reason you see this warning saying only they are applicable or they are valid in normal interface when the energy is arriving at a normal angle to the interface. There is another thing, we call it synthetic seismogram or convolutional model. That's what we know as the convolutional model. You acquired your data, you acquired such data, you want to tie them, you want to make a tie between your data and also a will you have. Probably there is a will, and that's very common in oil industry. Wherever there is seismic, probably there is a will. How you tie them? How you tie these two different information, seismic and will data? There is a process called will to seismic tie, and it can be done through synthetic seismogram, through the generation of synthetic seismogram. Here is the lithology or the ETH model you have. It's series of sand and shale, and each one has specific velocity. So this is the velocity in the shale is a bit higher than the sand. This sand is way more velocity than this sand, is even higher velocity than this shale. So that this sand is different than this sand since they have different velocities. And they have their own density too. You multiply them together. If you multiply them together, multiplication of velocity with density gives you acoustic impedance. That's the impedance. So this is the acoustic impedance. Then you create reflection coefficients using this equation. So density and velocity of this layer, density and velocity, density times velocity of this layer minus density and velocity times velocity of this layer divided by their sum gives you this one. Why it's minus? Why it's negative? Why it's in this direction? Because the acoustic impedance in this layer is lower than the acoustic impedance in the upper layer. So it gives you a negative reflection coefficient. Why it's negative? Because this term is higher than this term. So total, the reflection coefficient is going to be a negative sign. Here, this one with this one, with the upper one, it gives you this one. It's positive because this is higher. And how big is it? It depends how much difference between these two layers, how much the difference in acoustic impedance. If the difference is small, as you see here, the reflection coefficient is going to be small. And this is your source. This is what the hammer hit. That's the time function. This function is basically what energy you send to the ground. That's the energy sent to the ground, whether it's dynamite, Vibroseis, or whatever is it, has some characteristic. So this is one of the some characteristics of source, and we convolve it. Yani it's convolved with the earth. Convolution is complication. It goes convolved with this reflection coefficient. So you see, I'm multiplying this one or convolving it. It's not truly multiplication. It's a more complex mathematical equation than simple multiplication. Convolution is a mathematical term. So I'm convolving this one, this source function, with this reflection coefficient. So I see this one. I see that this reflection. This one gives me this color. The smaller they are, the smaller this is gonna be. You see? But I cannot differentiate them. I get this total one. I'm summing them. I'm summing this one with the other color, with the reflections. These are reflections from each interface. This is an interface. This is an interface. I have 4 interfaces. That's the total trace I get. This is the trace. That's the model I get. But I'm saying, so this is example. This is the source pools. That's what you see here. This is the reflectivity series. That's the one. This is the trace, seismic trace you get. How you make the tie now? How you tie your seismic with the well? Since you during the well drilling part, there is another process. They name it logging, well logging, and they send some type of equipment along the path of the well, and they record some type of information. They record the density of the rock. They record also the velocity of the rocks. So you get these two informations. You get these two information. The only thing you don't know usually is this source function or source pools. You try to make it similar to what you think is used during the seismic acquisition. What was the source function of your real source, whether it's a Vibroseis or a dynamite? You generate your reflection coefficient, convolve this reflection coefficient with the source, get your trace. At where the seismic is, you compare this one. You compare this one with the seismic traces, with what you see, for example, here. Let's assume that there is a well. Let's assume that there is a well like that. Oh, my drawing is bad. Bear with me. So there is a well. Here you generated your synthetic seismogram. Ignore those spikes. You compare this one with the nearby traces. You compare them. You see, okay, what's the difference between a synthetic seismogram and the real seismogram? And you can make good match then. And it's used a lot. The geologists use it a lot too in oil industry. So that's the basic idea of synthetic seismogram. Interfaces. Shall I go to this? This is not very common because the pools is single pools. So this is, you see this one? It's a pools. But sometimes it happens that a multiple get interfered with a primary. A multiple get interfered, a reflection, a pools reflected or seismic source is reflected from the going as a primary, which can interfere with a multiple, and it might destroy the overall signal because they combine together either destructively or in destructive way or constructive way. So here we have two cases. The difference between this case and the lower case, in this case, the velocity is increasing. The velocity is lower, then higher, then a bit more higher. Whereas in the lower case, the velocity for first and the lowermost layer is the same, but the velocity for the middle layer is higher. So what happens? What happens in this case? An energy, a pulse is arriving to this interface, whereas there is another pulse coming from this second layer, which is this one. So this one is moving. So this is coming. One is coming, and this one is moving, or even they are moving together. So this is reflected from the first layer interface, whereas 2 is reflected from this interface. That's it. You combine them together. So part of it gonna be destroyed. Part of the signal original source will not be the original shape of the function. That's also here. You see here, each one have a different shape, but I combine them together, I get this final product or final trace. If I keep decreasing the thickness of the middle layer, they can be combined in a way which make my final outcome very large. So I get very large, or in the other case, they can be combined to very small one. So they can be interfere together, reflection from different layers interfere together in constructive or destructive way. Then comes the point of how much the thickness of the layer supposed to be if I want to resolve it. If I want to see it, how much it's supposed to be thick for the seismic wave to resolve it. It's supposed to be quarter of the wavelength of the seismic source. So this thickness, to find it perfectly, to get two different reflections without much interference, either in constructive or destructive way, the thickness of this layer must be greater than quarter of a wavelength of the source energy. That's the source energy, characteristic of the source energy. Otherwise, you cannot resolve it. You cannot detect two different reflections. You cannot find two different reflections, 1, 2, because they get interfered totally in constructive way, and they show up as one reflector, one big reflector, one like big, something like that. Or they interfere destructively, you will find them as nothing, straight line. So one of them constructive, the upper one is constructive, the lower one is destructive. Why they are different? Because the acoustic impedance of those respective layers are different. The point here, what's the minimum thickness is? The minimum thickness is supposed to be quarter of a wavelength. So that's a good point. How I can get better data? How I increase the resolution then? I send higher frequency, because wavelength, the higher the wavelength, the smaller the smaller this value is, the wavelength. Let's say I want to make my resolve even 1 meter. Even I want to make or resolve 1 meter thickness of a layer. So my wavelength supposed to be how much? 4 meters. My wavelength supposed to be 4 meters. The wavelength supposed to, how I can get this wavelength or make it so? I should send specific type of frequency. The frequency of my data is supposed to be of a specific type. If I increase the frequency, I make the wavelength smaller. You know, this is general information to you, and the frequency is related to wavelength. The higher the frequency, the shorter is the wavelength. So if I want to make my resolution half meter, my wavelength is supposed to be 2. Quarter of 2 is half. And how I achieve this goal? Increasing the frequency. But there is a drawback. High frequencies high frequencies, they are easily absorbed by the earth. Earth eat them. So they cannot go very deep. So if you send very high frequency, then there is a limitation in depth. It's a general rule of thumb that Earth is acting as absorber of high frequencies. Whereas if you want to go deeper, penetrate deeper part of the Earth, make your frequency lower. But if the frequency is very low, it means the amplitude is so the wavelength is so high. The wavelength is so high, then what happens? You lose resolution. So there is this trade-off between depth of penetration and resolution. For example, earthquake waves, their frequency is very, very high. Sorry, very, very low. Their amplitude is so high. So that's the reason I cannot make good detailed resolution of the Earth subsurface. I only can see big pictures, big layers, core, mantle. They are big features. But for seismic case, a seismic reflection, my energy, the energy type, no. Naji is asking, high frequency means low energy? No. High frequency energy is meant how strong you hit. How strong you hit. It does not mean how, for example, for the vibrator, let's go back to the vibrator. How you increase the amplitude? Because it's moving. Okay, let me bring some toy which vibrates. Let's check the earth with small toy. The amplitude is nothing. The energy is nothing, but still sending the same frequency. Let me right now bring a vibrator. It's huge. Its weight is high. It's shaking the ground. The energy is high. The amplitudes are high. The bigger the vibrator you make it, the higher the amplitudes are. The higher the energy is. But it's also sending the same frequency. So make this distinction between frequency and amplitudes. But there is this trade-off. If you want to go deeper, even if you send high frequencies, they halfway or even in the shallow part of the earth, they get absorbed. They cannot travel. So distant earthquake we record, for example, an earthquake happened, let's say Japan, somewhere else, and got recorded by the instruments we have in Oman, the seismic network we have in Oman. Their frequency is almost like half hertz, or less than half a hertz. There is 0.00 something. That's their frequency, 0.01, 0.0. It's very small frequency. Their amplitude is so high. Not amplitude, sorry, wavelength. The wavelength is related to frequency. You record them, but they give you big picture of the earth. They will not give you detailed analysis or detailed resolution. Whereas in seismic refraction, I can send energy because I'm not penetrating very, very deep part of the earth. So don't make these assumptions that seismic reflection can give you everything. You can go to the center of the earth and get very detailed image. No. There is this trade-off at the end of the day. You need to make a balance between the frequency you send and the resolution you want to get. That's also one of the reason, again, we don't want to send 500 hertz. We don't want to my vibrator to keep vibrating and moving from 6 hertz to 500 hertz within short span of time, within 10 seconds, like, because high frequencies, they will be lost halfway. Let's complete this part. Bright spots. This seismic section, this is the bit C. Do you remember when I said bit C or C bit is good reflector? because the acoustic impedance is so high, or so the contrast between them is big. The difference between the sea layer or sea column and the sedimentary rock is so big, it generates high amplitudes. But in oil fields, whenever there is like oil and gas, they change the acoustic impedance of the rock. This change will make the contrast between the reservoir layer and the surrounding way different in terms of acoustic impedance. And this thing will let you easily sometimes identify if there is a reservoir or not. When I say a reservoir, a rock which contains hydrocarbon, either oil or gas, and you can easily detect them. So this is type of a reservoir. It's right away telling me, oh, there is some fluid there. Those fluid made a change in the acoustic impedance of the rock, and their acoustic impedance between this rock right now and the surrounding is so different. The amplitudes recorded are high. There is also this line because this is an erosional surface. This is an erosional surface. You know what's erosional surface by now. Erosional surface, you studied it in geology. The acoustic impedance along this line is so big, it generates this strong reflector. We'll see some examples. For example, here I see bright spot. All of these things, they are called direct hydrocarbon indicators. Another interesting thing is flat spot. You see this flat spot? There is another flat spot. There is another flat spot here. This red one. Another one here. Can tell me what those flat spots indicates? What they indicate? Said, what do you think? Said Shamahi. Said, are you from Sur? Said, can you listen to me? Maybe my lecture was boring. He sleep. Anyway, anyone can answer what they represent these flat spots? What do you think? This is also a flat spot. Wow, really interesting flat spot. They are direct hydrocarbon indicators. Actually, they represent fluid contact. They represent fluid contact. What's fluid contact? Oil beneath oil is water. Gas beneath gas is oil. Those contacts usually are flat. Fluid contacts are usually flat. So we find these features. We find these flat spots. We find bright spots too. We find sometimes dim spots. Dim spots because this is so strong, so bright. This is so bright. And then there is no more fluid here. No more, there is fluid probably, but no more gas, let's assume. It becomes water then. This change or this phase change between gas to water, there is a transition from high amplitude to low amplitude. And somewhere in between, there is a dim spot, this dim spot. The amplitude is almost like zero. This is high amplitude. This is very low amplitude. In between is zero. They are really good. A lot of the time using these things, you can identify if there is probability of oil and gas. So this is a bright spot. Why they happen to be here? Why not here? Why not in this syncline, but in the anticline?
Because the anticline forms a trap, Doctor?
Yeah, it forms a trap. So oil cannot stay here. It goes up, and we assume that this is a seal rock. This is a shale, probably. The upper part is a shale. So this part is shale, which is seal, and this is the reservoir. This is the top of the reservoir. But the oil then comes from down here, moves up deep, and get trapped here. It also get trapped here. And I get this flat spot because in here is right now oil, probably, and below that there is water. And the acoustic impedance in the rock which contains oil or water is different. And I get those flat spots. I find it in some places. In here, this is some data. I worked with this data, but interesting. You see, geophysics brings a lot of things to you. Again, here, this is a reservoir. This is also a complex reservoir. There is a fault here. This is a fault, the one I'm drawing. And they trapped in this area. So if I draw the structure, this is the steel, this is the reservoir, and the oil is coming from down below, get trapped here, and forms this flat spot. That's the flat spot. And this is my reservoir, the trap system. This is anticline trap system. This is a fault-assisted trap system. There are other things you can use for seismic for. For example, this is some place with a lot of risk from earthquakes. It's an area prone to damage from earthquakes. And they located them. They located where the earthquake happened, the XYZ location of those earthquake in the subsurface, but they don't know why it's happening. Why there is earthquake there? What's the reason behind these earthquakes? They did seismic survey. This is the seismic survey line, and they found that there is a fault. That's this fault, active fault, and all those events, seismic events, earthquake events, the color represents how big or small they are in terms of magnitude. Are they big earthquakes, small earthquakes? So you see one of them is magnitude 6. It happened in 87. The big blue one, big pink, sorry, one. So, okay, how I know that right now that, oh, there is a big fault. This fault is active fault. It keep moving. There is a stress along this fault which get released, and an earthquake happens when the energy is released. So maybe those events that I try to expect or guess where they are in this seismic section, maybe they are here. You see, this is somehow the basement. That's the basement. These are sedimentary rock. Upper part are sedimentary. And that's the reason you see layering within the sedimentary rocks. Whereas the basement rock, they have chaotic reflection style. There is no continuous reflections, whereas it's discontinuous. Continue for some time, discontinue it again. We call this feature chaotic. This is industry style, and this is made, this seismic data acquired using Vibroseis. This type, the one you see, it goes up to 50 meters. This is going up to like 7 kilometers. This is made by hammer. The hammerhead cannot send a lot of energy. It goes up to 50, 40 meters. This is mini a type of source, small vibrator. it goes up to like 600, 700 meters. So compare them, and as you see industry style Vibroseis, they go very, very deep. Let's talk a bit about 3D seismic. There are different type of seismic data, 2D or 3D. The trend nowadays is going along the 3D. Everything's supposed to be 3D. One of the difference between 2D and 3D is that you can take a line in every direction. So this is a cube actually. It generates for you a cube of data instead of one line. And you can analyze it in many different ways. For example, you can take a cross line. That's one line. You see this line? This might be a cross line. This might be an inline. You see this line here? The inline is along where the vibrators are moving. The cross line along is the cable line, the Jufun cable line. The vibrator moves in the inline direction. They make shot and move, keep moving. Whereas the Jufun's cables is in the inline, sorry, in the cross line. Cross line, that's the cross line. This is the inline where the vibrators move. You can take even an arbitrary line for 3D, and a line like the one you see here. This is an arbitrary line. You can even take a time slice. This is a time slice, a horizontal line. This is a time slice. You can take a time along a surface. And what you make, you go, okay, you see this surface, I interpreted that surface. This is the surface I interpreted. Give me the amplitude along this surface. Give me the seismic amplitude, extract for me the seismic amplitude along this surface. It gives you something like this. So this is surface slice. This is what you see here, time slice. Random line, that's the random line. This is the cross line. That's the cross line. This is the inline. Whereas it's not applicable to do this analysis in 2D. 2D is one line only. That's the advantage of 3D. But yeah, there is a cost involved with the 3D. Here is it for 3D acquisition. For example, you make a plan. Oh, I acquire my data like that. So you make a suggestion or a planning. I make this green, these blue points where you put your Jufons, whereas these red points where you put your vibrator points. Vibrator go and vibrate at these points, or probably even a dynamite shot is made at that point. This is your initial conception. That's how you think things supposed to be. But in reality, before going to the reality, how then I acquire the data? How I get my seismic traces? It's made through some process we already talked about it called CMP, common midpoint. Common midpoint. So these green dots you see are common midpoints. What are they? You see this one, this receiver blue and this red. These two have a midpoint. Have one midpoint. So receiver, source, that's their midpoint. If I imagine how many midpoints, so this source fired right now. It has one midpoint between this one and this one here, between these two. A midpoint between this one and this one. A midpoint between this one and this one. There are too many midpoints along this one and this one. So this source and this source, red point here, and this receiver, the last one, have some midpoint, a trace here. A trace in the middle. If I draw them all, it becomes something like what you see here. There are more midpoints in the middle because I can make a lot of midpoints than in the flanks, in the sides. If I make a plot of how many midpoints are in the middle, they are high. So this green color bar you see here, it's saying something about the fold. Fold, how many midpoints in that rectangle, in that bin? How many midpoints in that small rectangle? So this midpoint probably between this receiver and this one. Also this resource, this GPhone. Between this one and this source here you find and this GPhone. This is the midpoint. You see, this has a lot of them, a lot of combination I can make. Whereas this one here, it has low folds because that's how it's flank. That's in the middle. This is your reality. This is what you make initially as a planning. But when you go to the site, you cannot deploy it like that because you see there is a wadi. You change it then. If you check here, you say there is no in there, there is no receiver. There is no receiver here, no blue dots, because that was in the wadi. There are not much shots. There are just 2 shots in here. They are not in along the line. They skip the line. This is the actual survey. You make a lot of adjustment. Those adjustments are made due to change or due to obstacles on the surface of the earth. Logistic problems probably, but most often because of constraints or obstacles you find on the surface. Here, I supposed to have, in my planning, I supposed to have 1 shot here and another shot here, but instead I dropped them because they are along this valley. Along this valley. So I dropped them. I stop here. I delete this slide too. That's enough. Because having 5 minutes left, I supposed to teach you in the course. If in the book, if you read the book, it goes to something called sequence stratigraphy. Don't read that one. Don't go study those parts. Everything from the book except these slides. I wanted to explain. Sorry, these slides. Seismic 3D seismic acquisition. 3D seismic in general. Maybe I send you, thus far we finished seismic reflection. We need to move forward. 5 weeks left. So in these 5 weeks, we need to finish gravity. We need to finish resistivity technique. And let me think of what other technique. Let me go back to my outline. And which one's supposed to be? The next one going to be gravity method. Do you have any questions? Any questions related to what we have said or talked about? I saw you see I made some few updates to the slide. I uploaded again, delete the previous one. Any question, guys? If you don't have question, I will close. But before closing, these are the lectures. I'm giving you a project. I will be sending you a project. I will also make some short videos explaining how you make seismic interpretation. I don't ask you to use a software because that's going to be tough for you in one sense that your computers usually are weak, not like you are working with small laptops. So seismic interpretation actually requires a soft or high computer power, computer with strong CPUs and memory. So maybe your small laptops cannot handle these things. So for this project, I group you into teams. I will see how many members are in one team. I probably even mix you, female, male, maybe. I know a lot of people here, at least my friends, they married from they married their colleagues from this group working. Yeah, maybe you also marry one of your colleagues too. Who knows? So I will group you into teams. You need to work in this seismic interpretation project, the teamwork project. I will explain everything what you need to do, but not using software, doing it manually. Some of the lines you see, they were already interpreted. There is a reservoir there. Your task is to make an interpretation, to draw a map of this reservoir, to draw a map, a 2D map. It's a 3D data actually. The data itself is a 3D, so these are inline across line directions. And at the end, I think you will like it. Will enjoy this project. It's a real project. And students who usually join this competition, probably you have heard of it, IBA, Imperial Barrel Award. They do something a bit similar. At least at certain stage, they do something which involves a seismic interpretation. And the data they receive, sometimes it's 2D, sometimes 3D. I'm receiving how many questions? It's a mix of multiple and some essay too. But 30 multiples and some essay questions. 30 questions multiple and some essay. You like essay? It's a bit advanced level course. You should have some essay. Let's make some small essay. Yeah. Actually, usually my multiple choices are a bit tricky too. You will see that. Maybe you lose more questions with the multiple choices and get better marks in the essay part. But as I said, this is not very low level course. And I think that you need to have at least some essay questions. Wish you all the best. Please all attend because there is no makeup. Without valid reason, never ever make a makeup. So do your best, study today very well. Tomorrow is the end of the day. Next week we have 2 days holiday. So I might ask you to work on this project. If you make questions of complete sentence is better. What do you mean, Anwar? If you make questions of complete sentence is filling gaps, you mean? Filling gaps. Let me see, maybe I change them, but there is no time right now to change. Tomorrow I have a big meeting before the exam. Multiple choices. Ahmed, multiple choices are 30. But they are part of it is also easy.
دكتور, what is about time?
ساعة ونص. مروة I said.
دكتور, ساعة ونص يعني كامل ولا مدة الاختبار فقط ساعة؟
لا, مدة الاختبار ساعة ونص. كافي؟
ايوه كافي.
طيب. Reflection is not included, Marwa. I sent this information way like in week probably 5. They confirmed if the date is changed, the exam includes stay the same material. If you don't have questions, the time passed. I got extra 1 minute from your side. So I first of all stop the recording. Going on. You can leave if you like. Goodbye, meet you tomorrow. The exam is on module. You'll have it on module.